Hello everyone. We will solve one problem from the university question paper which appeared for 6 marks. In this, there is a double pipe heat exchanger which is operating in counterflow mode, which is cooling an oil flowing at the rate of 10,000 kg per hour with specific heat 2095 joule per kg Kelvin. It is being cooled from 80 degrees Celsius to 50 degrees Celsius with the help of cooling water which is flowing at the rate of 8000 kg per hour and entering at the temperature of 25 degrees Celsius. Overall heat transfer coefficient is 300 watt per meter square Kelvin. Specific heat of water is 4180. We need to calculate LMTD as well as heat exchanger area when this heat exchanger is operating in parallel flow as well as counterflow configuration. We will also compare these areas on the percentage basis. So let us first of all write down the given things. So in this case, m dot h is 10,000 kg per hour. So that is equal to 10,000 divided by 3600 kg per second. All right. Afterwards, we have Cp. Okay, we also have m dot c, and that is mass flow rate of cold fluid. So that is 8,000 kg per hour. Then we have hot water inlet temperature. We have m dot c, and then it is 8,000 kg per hour. So that is 8,000 divided by 3600 kg per second. Thereafter, we have hot fluid inlet temperature, that is 80 degrees Celsius, THI, which is 80 degrees Celsius. Then we have THO, which is 50 degrees Celsius. We have TCI, which is 25 degrees Celsius, and TCO is not known to us. So now immediately we understand that because 3 out of 4 temperatures are given, so it implies 3 out of 4 temperatures are given. So because of that, we have to use LMTD approach, and also it has been asked in the question itself. Okay, then overall heat transfer coefficient U is 300 watt per meter square Kelvin. And the specific heat of hot fluid is Cph. It is 2095 joule per kg Kelvin, and Cp of cold fluid, that is water, it is 4180 joule per kg Kelvin. Fine. So now the approach is clear. We will just get clarification about the mass flow rate. So 10,000 and 8,000. So we will start the calc for this. So 10,000 divided by 3600, so 2.77 kg per second. That's the mass flow rate of hot fluid. So 2.77 kg per second, and then 8,000 divided by 3600, 2.22 kg per second is the mass flow rate of cold fluid. Now, in order to provide the solution, what we need to do, we directly need to establish the energy balance, which is according to the first law of thermodynamics, and we now know how to establish it. We can do it simply by putting down, I will just write it here, energy balance. This energy balance is necessary so that we can obtain this unknown temperature TCO. So energy balance tells us that whatever heat rejected is there because of the hot fluid, all that heat is received by the cold fluid. And this is again sensible heat. Remember, there is change in temperature of cold fluid as well as change in temperature of the hot fluid. So it means that this heat transfer is sensible heat transfer. If it is sensible heat transfer, which means we can quantify that, immediately it should come to our mind with the help of this expression mc delta T. So now this is sorted. So for the hot fluid as well as for the cold fluid, we will write the mc delta T equation. So what do we get here? M dot H into Cph into delta Th. This will be equal to, or in a simple general form, I will write it, mcp delta T of hot fluid will be equal to mcp delta T of cold fluid. So m dot H into Cph into delta T for hot fluid will be inlet temperature minus hot fluid outlet temperature, and for the cold fluid it will be m dot C into Cpc into TCO minus TCI. Now we will put in the values. So m dot H 2.77, so Cp of hot fluid, it will be 2095 multiplied by THI 80, THO 50, m dot C 2.22, CPC 4180 multiplied by TCO, unknown quantity. TCO is unknown, TCI is 25 degree Celsius. Excuse me. So now we will solve this. Ultimately, because of this, we will be able to obtain TCO. So TCO will be immediately whatever is this entire quantity divided by this product plus 25. So unlike our previous video, I will show this directly. I will just need the input quantities. So 2.77 into, just give me a second, into 2095 80 minus 50, or in simple words I will do it like this: 2.77 into 2095 into 80 minus 50 divided by, we need to divide it by this entire product of 2.22 into 4180, 2.22 into 4180. So whatever this is, we will add 25 to it. This is how you will get the cold fluid exit temperature, 43.76. So TCO is 43.76 degree Celsius. So we have this TCO, and now we will need to calculate the LMTD both in parallel flow as well as counter flow configuration. This I have explained in my previous video. You can go and watch it. So for parallel flow, I will make a simple drawing immediately, as well as for counter flow. I have already explained how to prepare this drawing, so I will not consume time in explaining that once again. So this is the hot fluid on both the sides. The only difference will be in the cold fluid. In case of parallel flow, cold fluid will flow like this, while in case of counter flow, the cold fluid will flow like this. So we have already marked up, we will already have marked up THI, THO, THI as well as THO. Okay, my mistake, I forgot to write down the specification of heat exchanger. This is parallel flow and this is counter flow. Fine. So we have THI, THO, then we will have TCI, TCO for parallel, and for counter this will be the TCI and this will be the TCO. All right, so delta T1 in case of parallel flow will be this much, delta T2 will be THO minus TCO. For counter flow, THI minus TCI will be delta T1, while THO minus TCI will be delta T2 because of their flow configuration. So we will immediately start calculating that. Delta T1 will be equal to THI minus TCI. So THI is 80, TCI is 25. You do the subtraction, so that comes out to be 55 degrees Celsius. Delta T2, it will be this THO minus TCO from the diagram itself, and that's why diagram is important. So THO is 50 degrees Celsius and TCO is 43.76. So you do the subtraction. I have done it on my calci. That comes out to be 6.24 degrees Celsius, and that is why LMTD for parallel flow, so delta T LM for parallel flow will be equal to delta T1 minus delta T2 divided by ln of delta T1 upon delta T2. So let us substitute the values. 55 is delta T1 minus 6.24 divided by ln of 55 by 6.24. So 55 minus 6.24 divided by ln of delta T1, that is 55, and 6.24, that is delta T2, bracket complete, 22.40. This is your delta T LM in case of parallel flow. I will just confirm it. So it is 22.40. For those people who do not have this ES type of calculator, let us say they have either 100 ms or 991 ms or this 82TL calculator, I can show you that same thing, how to do that. 55 and 16. You just need to be careful with the brackets. So in the first of all, numerator 55 minus 6.24, numerator bracket complete, divided by, you can directly actually go with ln, or if you want to feel safe, you can put opening bracket ln of, now ln itself has its own bracket, so ln of 55 divided by 6.24, close the bracket of ln, close the bracket of denominator, you will get the same answer, 22.40. so no confusion there. Any calculator you use, it doesn't matter, the answer will come out to be the same. So now you have delta T LM for the parallel flow, and now you know that heat transfer is equal to UA delta T LM, whether it is parallel flow or it is counter flow. Now what is Q? Q can be either Q hot or Q cold. In this question they have not asked us about the heat transfer rate, so we will not calculate it separately. Actually we can directly obtain it from this quantity. Either you can calculate QH or you can calculate Q cold. So 2.77, 2095 and 80 minus 50. I will simply use it here. We know that Q is equal to 2.77 into 2095 into 80 minus 50. So that is 2.77 2095 into 30. So 1740 174.09. 22.77 into 2095 into 80 minus 50. So 174094.5. These many watt is the heat transfer rate. We can use this quantity in this expression now. So what do we get? It implies that 174094.5 is equal to UA delta TM. So U, it has been given as 300, I suppose. So yes, U is here. We have written it in the given things. So 300 into area of parallel flow, unknown quantity. Delta T LM we just calculated 22.40. So it means that we are now arriving at our final answer. Area of parallel flow 174094 322. Okay, so the answer, this, it can be divided by, denominator will be U and delta T LM. So 300 into 22.40. So the answer comes out to be 25.90 meters square. This will be the area required in the parallel flow configuration if we use that heat exchanger in this configuration. Fine. Now we can go with the counter flow arrangement. So we will repeat this exercise and we will do it as quickly as possible. Delta T1 for counter flow, it will be THI minus TCO. So THI is 80, TCO is 43.76. I again advise you to go with the calculator. Even I am keeping one calculator by my side. So 80 minus 43.76, that gives you 36.24. Side by side, if you make the calculation, that will make your understanding concrete. Counter flow THO minus TCI from the diagram. I am not referring, I don't need to remember the formula. It will be directly available because of the diagram, and I will not be making any mistake in this because diagram is there in front of me always. So THO, that is 50. TCI, that is 25. So your delta T2 is 25 degrees Celsius. So because of that, LMTD, delta T LM for counter flow, delta T1 minus delta T2 divided by ln of delta T1 by delta T2. Only watching the video will not help, you should do it side by side. So that is why delta T1 is 36.24 minus delta T2 is 25 divided by ln of 36.24 divided by 25. Let's do it in the calci. I will use the simpler mode, 36.24 minus 25, and I have already shown how to do it on the other calci. So ln of 36.24 divided by 25. It is just that this kind of calci becomes handy, somewhat convenient. So 30.27. There is no problem with 100 ms or 991 ms, just that this calci is simpler to use. So 30.27 degrees Celsius. This is delta T LM for counter flow heat exchanger. Fine. So again we will be using same philosophy. Q is equal to delta T LM. Q is equal to UA delta T LM in case of counter flow. Fine. So now how much is Q? It will remain same, 174094.5 This is equal to U is 300, then area of counter flow multiplied by delta T Lm 30.27. So it implies that area of counter flow, we will calculate it now, 330.27, 174095.5 divided by 300 into 30.27. 19.17 is the answer that we are getting. So area of counterflow heat exchanger required for the same amount of heat transfer, as we can see, this area is lesser in case of counterflow heat exchanger. So that is the benefit of counterflow heat exchanger. As we have also discussed similar thing in the previous video. Now we will calculate percentage change in area because of the parallel and counter flow. So that will be obtained as parallel flow area minus counter flow area. Remember, logically we are checking how much more area is required in parallel flow, so we are comparing it against counter flow. So that is why there will be counter flow heat exchanger area in the denominator. So 25.90 minus 19.17 divided by 19.17. So let us calculate it. So 25.90 minus 19.17 divided by 19.17, entire term multiplied by 100. So 35.10%. This multiplied by 100. So it means that 35.10% more area will be required in parallel flow heat exchanger. This is your percentage delta E, percentage variation in area of the heat exchanger required. So this problem is from the university question paper. I have provided this solution. I don't have the solution received from the university. If there is any concerns with the calculation, you can let me know in the comment box. I hope this video has been helpful to you. We will meet in the next video. Thank you.